A comparison between textual similarity functions applied to a query library for inspectors of extractive industries. Hello, my name is Junior. Here's my contact if you'd like to reach me, and my advisor is Professor Dr. Eduardo Nunes Borges. To understand the problem, we need to know that the weld inspection is an important part of the process in the maritime industry, because it ensures the integrity, the performance, and the safety of the welds carried out. That's why these inspections can only be made by certified professionals. There are different institutions like these 3 Brazilian institutions, an American Petroleum Institute, and each institution has its own web page to search for certified professionals. The institutions use simple search methods like substring equality. This simple search method does not work well for our study, so we need another approach, because the names and registration numbers of professionals from optical character recognition can have some errors of detection. This example shows how one of the search tools work. We search for the name Pedro, and the search returned 8 professionals. And looking at the result, we can see that the search is using substring equality. Now thinking about our use case, we use the same name, but with one mistyped character. This time we do not have any result, because the used search method does not consider mistyped words. If it does not work with a simple example, we cannot rely on it. The example has shown us that we cannot depend on the search tool available on the institution's page, because it is not good enough to handle our queries. So the solution found was to unify the different databases on a single basis. Also, for security reasons, we didn't want to give access to the database for other services. So the best way found was to make a query available through a RESTful API. After all, an API can be consumed by any programming language that can perform HTTP requests. The final step was to deal with typing errors and variations in writing, and in order to solve that, we choose to apply a character-based similarity functions who are lexically similar if they have a close character sequence. First of all, we need to know the n-gram concept, because the used similarity functions are based on them. So basically, n-grams are a sequence of n elements that appear in a text. In this simple example with 3-gram, the word computer becomes a set of 6 strings that have 3 characters each. The used main 3-gram based functions are represented with these 3 equations. The similarity equation is the ratio of the intersection of 3 grams of string A and B with the union of string A and B. The word similarity equation is the ratio of the greatest similarity between the string A and any of substrings of string B, and the sets of 3 grams of string A. This equation does not consider the word boundaries. Also, string word similarity is similar to word similarity, and this ratio is between the greatest similarity and the union of the same sets of 3 grams of string A and B. For better understanding of the used similarity functions, we have 2 strings, A and B, that we want to know their similarities. First, we transform these strings in sets of 3 grams. Note that string B has 2 words, so also we break the B into B1 in B2, and define n equals to 2 that is used in this formula. To calculate the similarity between A and B, we take the intersection of sets A and B and the union of the same sets. So we apply the ratio between the results, 6 and 15. Then we have the similarity value of 0.4. Now to calculate the word similarity, we take the max calculated value between they grade the sequence of sets A and B, B1, and they grade the sequence of sets A with B2. So the max value between 6 and 0 is 6. Next, we count the number of sets from A, that is 8. And finally, we calculate the word similarity, that is the ratio between these two values, which is 0.75. For the strict word similarity, we take the max calculated value and the union of the sets A and B, and apply the ratio between them. So we have the value of 0.4 also. Related works. In work number 1, they needed a way to share research data in electrophysiology, and they did so by developing an API where the research data can be saved and found. In work number 2, they needed a way to make climatic data available from the Center for Weather Forecasts and Climate Studies. Their data is stored as binary, and often researchers needed this data in different formats, so they developed an API to tackle that problem. In work number 3, they had a working system called Freud, but as the data increased, they needed to make some improvements. So they developed an API which could make search methods available and also let other researchers to upload their own data of mass spectrometry. In work number 4, they tested 2 PostgreSQL models to make a full text search functionality on opengeocoding.org. That is, a community project for assembling geocoded addresses. They found that one of them wasn't good enough to handle mistyping words, and that the other wasn't fast enough to apply in an autocomplete full text search. In work number 5, they have a widely used open access database of curated non-redundant transcription factor binding profiles, and they developed a RESTful API to which they named Jasper to make available data in different formats according to the used query. All these related works shown seek to provide data in a more accessible way, allowing other systems to search through them in a simplified way. Methodology. So we developed a relational data structure based on the data that we found, a scraping algorithm to make requests on the different data sources, a PDF reading algorithm who extracts tables with all the information that we need from different inspectors, a RESTful API for searching the database using the similarity functions, and at last we evaluated the results to know how good it is for the use case. Here we show how the system works. We gather data from different approaches. The first from the web, with a scraping job, which gathers data from American Petroleum Institute, FBTS, Abraco, and Abenji. The second is a PDF file with a serverless function that runs when it receives a document. The data is saved on a PostgreSQL database, and the API with Node.js searches the database according to the used route. So the docs API is the documentation route. The inspector API inspector route is where the similarity functions are used. And the inspector with the parameter ID, it finds just the specified inspector. The evaluation consisted in using 10,000 samples. For each sample, we took the first name and last names, ignoring any middle names. In the first and last names, we replaced 1 and 2 characters randomly. With the generated name, we made a search with the limit of 20 documents. And for each name, we search with the 4 similarity functions. For each search, we save the time results on both API and client side. And at the end, we calculated the precision recall curve and the area under the curve for each used method. We define the relational data structure as shown, where an inspector has a name and can have one or more certifications in different institutions. Each certification has an institution linked to a registration number, a source to which it can be PDF or web, and a register date. Each certification can have more than one technique, where the technique has a due date, that is the date on which the technique is no longer valid, a type that corresponds to a technique identification, and the level assigned to the technique. So we ran the scrapping job, the serverless function, and they included around 48,000 inspectors, 74,000 certifications, and 85,000 techniques. All data took nearly 35.5 hours, with an average of 1.73 seconds per certification. Also, to evaluate the 10,000 samples, we took approximately 27 hours. So we plotted the precision recall curves for 1 replacement per token and 2 replacements per token. So the green line is the lavage time, the blue line is the word similarity, the red is the strict word similarity, and the orange is the similarity function. As we can see on both graphics, the similarity function goes best, comparing with the others, where with 1 replacement per token, it had almost 78% of precision. For 10 to 50 of recall. And for two replacement per token, it had almost 46% of precision for 10 to 30 of recall. Also, we can see that the lavage time function had the worst result with 1 replacement per token. But with 2 replacements per token, the word similarity, lavage time, and strict word similarity got almost the same result, with a precision between 20 and 30 for 10% of recall. The similarity function had the best time result with 1.03 seconds of response API side, and the lavage time the worst time with 1.63 seconds. For the calculated mean average precision and the area under the curve, the similarity function had the best mean average precision and area under the curve for both 1 replacement per token and 2 replacement per token, where for the mean average precision for 1 replacement per token, it got 0.8, and for 2 replacement per token, it got 0.53. And for the area under the curve, for 1 replacement per token, it got 0.57, and for 2 replacements, 0.27. Works better when comparing with the other tested functions. Also, for the tested data, our system works fine, because the service that we'll be using this API is a work in progress. we don't have the real data available yet. So we don't know now if it will be good enough to handle the real data.